Hello, and welcome to Mr. Van Lowe's science YouTube channel. Today we're looking at chemistry, specifically calorimetry. There's definitely some overlap here with physics, including change in temperatures and changes in energy due to specific heat capacity. So, let's take a look here. Here's our first problem. We're asked to find the specific heat capacity. We should think about this in terms of specific heat capacity. Just FYI, this is a small typo. Oops. Enthralling watching me write capacity. There you go. Okay, so the specific heat capacity of aluminum is given by the mass of aluminium or aluminum, depending on where you're from, times the specific heat capacity of aluminium, times our change in temperature. Okay, so we solve this equation for C by dividing both sides of the equation by mass times temperature. And when we then get C is equal to the energy divided by mass times change in temperature. There it is. Okay, now all we have to do is plug in the values that were given in our problem setup, and here they are. And our final calculation will give then 0.90 joules per gram per degree Celsius, and that is the two significant figures. Okay, next we're asked to find the specific heat capacity. We're given the temperature change, 3.8 degrees Celsius. We're given the mass of the sample, 4.11 grams, and we're given the energy, 11.1 joules. Okay, so we just use the same equation that we had up here and plug in our values. And we find that we have 0.71 joules per gram per degree Celsius. And again, that is two significant figures. Our limiting factor on significant figures in both cases is given by temperature, which has two sig figs. Okay, next question. How much heat must be added to an 8.21 gram sample of gold to increase its temperature by 6.2 degrees Celsius? And we're given the specific heat of gold, or specific heat capacity rather, of gold, and that is 0.13 joules per gram per degree Celsius. Okay, so here it's very easy. We don't actually have to modify our equation at all. We just plug in the values and we get 6.6 joules for the heat energy added to the system. And that is, again, two significant figures. Right, number 4. Here we're asked to find the temperature increase if we add 40.5 joules of heat to a 15.4 gram sample of silver. And we're given the specific heat capacity of silver as 0.235 joules per gram per degree Celsius. Okay, so here we need to solve for our change in temperature. And we simply do that by taking our initial equation, Q is equal to mc delta T, and dividing both sides by mass times specific heat capacity. Okay, so there is the equation we need, and we plug in the values. And we find that we get a temperature increase of 11.2 degrees Celsius. And for this problem, we have 3 significant figures instead of 2. Nice. All right, next page. All right, for this page, we need to recognize, and this is very important, that the heat lost by an object in contact with another object will be equal to the heat gained by the other object. Okay, so the amount of heat energy transferred from one object to another will be equal. Okay, so here we have the energy of heating, the object or substance heating, equal to the negative energy of the substance cooling. Okay, and the reason why this value is positive is because heating something up is, by definition, endothermic, as you will recall from a previous lesson. And the reason why this value is negative is because losing heat energy is, by definition, exothermic. Okay, so now we have our positive and negative signs in place. Let's take a look. So, number 5. We have a sample of a metal that is heated up and then placed into a calorimeter that contains water. So we assume that our water is perfectly insulated and that when we place the zinc sample into the water, all of the heat energy from the zinc will be transferred into the water. Okay? So the temperature of the water is going to increase by a pretty small amount. If we calculate the temperature difference right now, you'll note that it is 2.5 degrees Celsius. Okay, just subtract our final temperature from our initial temperature, and that gives us 2.5 degrees Celsius. The specific heat capacity of zinc is 0.390 joules per gram degree Celsius. And we're asked to find the initial temperature of the zinc. Okay, so let's break this down. The first thing you will want to do is calculate the heat of the heat required for the temperature change of the water. Okay, and so that is going to be given by energy of heating is equal to the mass of the water times the specific heat capacity of the water times the temperature change required for heating our substance. And what we will then find is that when we plug in our values, we have 679 joules. And this value is positive because the water is heating up. Okay? So that then is going to be equal to the energy transferred out of our metal sample, our zinc sample. Okay? So the energy of cooling is going to be equal to negative 679 joules. Okay. We can now find the change in temperature of our cooling object by, again, using our initial equation, Q equals mc delta T, and dividing both sides by mass times specific heat capacity. Okay, so that gives us this nice equation. And we're going to plug in the energy of cooling and the mass of the zinc along with the specific heat capacity of the zinc. So that's an important step. We will then find that we have a change in temperature of negative 690 degrees Celsius. Negative 696 degrees Celsius. So to find our temperature change for cooling, we simply need to rearrange this equation such that our initial temperature is equal to our final temperature minus our change in temperature, which you will recall is negative. Okay, so what that means then, we're subtracting two negatives. What that means is we're going to add 696 to our final temperature of the system, which is 22.5 degrees Celsius. Okay, this is then going to give us 719 degrees Celsius, and that is out to three significant figures. However, this is problematic because that value is larger than the melting point of zinc. So in order to actually calculate this part of the equation, we would need to consider the phase change of zinc, which is above the level of grade 10 chemistry, but you will be looking at that in physics. So the setup for this problem is an issue because this is too big for the mathematics that you guys are required to know. So it's a problem, but you don't need to worry about it right now. Next year, grade 10 students. All right, number 6. The setup for number 6 is actually exactly the same as our previous problem. So if you want to pause here and take a look at the math, that's fine. I don't think there's a problem. I don't think there's a lot of value to re-explaining it, but this should be the mass of the gold and the specific heat capacity of the gold. That's better. So you go through the same process. Calculate the initial heat, calculate the change in temperature, then add the temperature change to the final temperature of the system, and you will get 163 degrees Celsius. So I'm going to zoom out, and if you would like, you can pause the video and look over the math. If you need to, go ahead. Last problem, slightly different. We have a 28.4 gram sample of aluminium. It is heated to 39.4 degrees Celsius, placed in a calorimeter containing 50 degrees of water. The temperature of water increases from 21 degrees Celsius to 23 degrees Celsius. So you might notice immediately that we have then two changes in temperature here. And that is normally the case when we're placing two objects with different temperatures into contact, okay? So we have the change in temperature of the object that is hot, and we have the change in temperature of the object that is cool, okay? So once again, we're going to first deal with the change in temperature of the water, and that is given by the same equation. So this is exactly the same start as we had in our previous problems. So we calculate our energy of heating, and that gives 418 joules. Our energy of cooling then will be negative 418 joules. So our aluminium is going to lose 418 joules of energy as our water gains exactly the same amount. Okay, to find the specific heat capacity of aluminium, we use this equation, and we plug in our values, and we remember that our temperature change is given by final temperature minus the initial temperature. And the initial temperature here is going to be the larger value. So if our object was being heated up, that would be the opposite. Let's just skip that. There we go. Okay. I made a spelling mistake. We're just going to abbreviate. It's easier. Okay, so there we go. We plug in our values, and we find that our negative signs are going to cancel out here. And we're then left with 0.90 joules per gram degrees Celsius to two significant figures. And you will note that this is exactly the same value that we calculated initially for aluminium. So, quick way to check your answers sometimes is to look at previous work that you've done. So you should definitely do that when you get a chance. If these two answers did not agree, that would mean I made a math mistake somewhere. And in fact, the first time I did this particular problem, I did make a mistake, and I realized it quickly and was able to fix it. I used the wrong mass here. So you may find other mistakes in my work, and if you do, please let me know. It's not uncommon. Okay, that is it, ladies and gentlemen, or anyone else listening. Hopefully you enjoyed the presentation and found it informative. Do not click subscribe, and have a great day.